Yeah, thank you very much for coming, all of you. It's super hot outside and it's also super hot inside. And on top of that, at 5 o'clock, Zhu Wu Zhang's talk will start in the number theory seminar. So there is quite a bit of competition this afternoon, both by the number theory seminar and the sun. But nevertheless, thanks Lillian for the introduction and thanks for the opportunity to give somehow the closing talk of this summer school. Here you see the theorem that I stated last time and for which I still owe you a proof. So what does the theorem say? We take a polynomial with m distinct zeros in the algebraic closure over a finite field Fq. We take a multiplicative character, of course a non-trivial one, and we want to estimate this character sum, and the bound we get is best possible. It's a square root cancellation in Q, and the implied constant depends on the number of distinct zeros. All right, and here is the proof. And we need 3 key facts, and I recall those. This is what we already proved, but let me just recall. Fact number 1 is a counting estimate. If we count xy in fq, let's say maybe even fq to the nu squared, such that y to the d minus f of x equals 0, and this is absolutely irreducible, then this is what you would expect, q to the nu plus O of q to the nu over 2, and the error term depends in a specified, but for us not interesting manner on f and d. Okay, that's key fact number 1. Key fact number 2, that's a very simple fact. That's something we had in the very first lecture. A number x is a dth power in fq to the nu star if and only if its norm down to fq is a dth power in fq. So that's very simple. And then also a very important fact is what's the shape of character sums over extension fields. And I write this down in slightly more general form. If I have a character sum over an extension field, chi of f of x, psi of g of x, we don't need psi for this theorem, but we need it in general. Then this is a sum of things, and you take the nth power, and how many things do you have? N plus m minus 1. In our case, n equals 0. And again, we don't know anything about a priori about the omega j's, but we do know what happens if you go up the tower. Then you just need to take nth powers of the omega j's. Okay, these are the 3 key facts, and if you take them for granted, then the proof is relatively simple. Okay, so let's start with the proof. So here is the proof. Okay, first of all, without loss of generality, assume that f is monic. If not, simply factor out the leading coefficient, and this doesn't change, as we know, the notion of absolute irreducibility. So without loss of generality, assume that f is monic. Okay, and so what we do is we consider, we consider all characters chi tilde in fq star hat with chi tilde to the power d equals 1. This includes our character of interest. The character chi is one of those. It has order d, but we take all of them of order dividing d, including the trivial character. Okay? And for every nu in n, we consider the character sum S nu chi tilde which is the sum chi tilde norm nu of f of x, where x runs in fq to the nu. So the norm goes down to the ground field, and then I can apply chi tilde. So this makes sense. And we know from key fact number 3 that this is minus. Did I include the minus? No, I forgot the minus here, but the minus is not so important. So it's minus a sum of m minus 1 things raised to the power nu. And these things depend, of course, on chi tilde in some way, as long as chi is not the trivial factor. For chi tilde non-trivial and certain omega j chi tilde in C, some complex numbers. Okay, but for the trivial character, of course, it's easy. So for the trivial character, well, then the trivial character says always 1 unless the argument was 0. And this happens if and only if there is a 0 of f. So this is just q to the nu minus the number of distinct zeros, so minus n. Okay? All right, so now comes the key step. So now we compute in 2 ways the following quantity, the number of all xy in fq to the nu squared, such that y to the d equals f of x. All right, let's call this r nu. All right, okay, there are 2 cases. Either y is 0, in which case x must be a 0 of f. So that would be the number of x in fq to the nu such that f of x is 0. And that cardinality, of course, is m, plus the non-zero cases. And so if there is an x such that f of x is a d power, then I get these solutions for y. So this is d times the number of x in fq to the nu such that f of x is a dth power. Okay, the first thing is just m. That's the number of zeros. And the second set counts dth powers in the extension field. And so I can just do this by taking norms. So this is plus d times the number of x in fq, well, star, I should say. Well, the star is, okay, it doesn't matter. Well, let's take the star, such that the norm of f of x is in fq star d. Okay, but this condition, being a dth power in fq, can be detected by the characters of fq of order dividing d. So this is m times m plus the sum over all characters chi tilde in fq star hat, such that chi tilde to the power d equals 1. And then the sum over all, just by orthogonality of characters, x in fq to the nu, it doesn't matter whether I put a star or not, chi tilde composed with the norm f of x. Aha, but this, so here I single out the trivial character. So this is S nu triv plus the non-trivial ones. Some chi tilde non-trivial S nu chi tilde. But as you can see, S nu trivial is just this thing here. So this gives q to the nu minus m plus m plus the rest. So chi tilde, non-trivial. And we know what these S nus are. They are certain sums. So minus sum j from 1 to, from 0, no, from 1. From 1 to m minus 1, omega j chi tilde to the power nu. Okay, as long as we don't know anything about the omega j's, this is totally pointless. But I said we want to compute this in two ways. This R nu, we know already what R nu is. This is the first key fact. So on the other hand, by the first key fact, we have R nu is q to the nu plus O f d q to the nu over 2. Now, if you compare these two, we see that this sum over the non-trivial chi's is O of q to the nu. And now we use the self-improving estimate. Now use lemma 4.1. And this tells us that each omega j tilde in absolute value is strictly bounded by q to the 1/2 with implied constant 1. So the counting estimate together with the bootstrapping lemma gives us a bound on the roots. Okay, and that's it. Now we just plug this into the third key fact. So for one particular sum, we sum up m minus 1 things. So now we take nu equals 1. So now take nu equals 1. And so the character sum S1 of chi, that's what we are interested in, is bounded by an absolute value j from 1 to m minus 1 q to the 1/2. And this is, of course, m minus 1 q to the 1/2. Okay, that's it. That's the proof. And we get a corollary for free. We can turn tables and reverse the argument, and in the same, so in this way, improve the counting estimate. The counting estimate gives an unspecified dependence, or it gives a specified dependence on f and d, but a bad one. We can improve this quite drastically. So the counting estimate improves automatically, and we get that the number of xy in fq squared such that y of the d to the d minus f of x equals 0 minus q is bounded by d minus 1 times m minus 1 times q to the 1/2. So famous example, due to Hasse, take d equals 2, f cubic, then you count points on elliptic curves over finite fields, and you get the Hasse bound that the error term is 2 minus 1 times 3 minus 1 times square root q, so that's 2 square root q, that's precisely the Hasse bound. So number of points on elliptic curves over fq is, so minus q is bounded by 2 square root q, and we get even the constant right. Yeah, that's the best possible constant, and that's what we get. Okay, and of course, this statement here, this is the Riemann hypothesis for the L function corresponding to this character sum. So for L S chi, in fact chi tilde. So All right, so this is the statement for multiplicative character sums. I will now state and shortly prove the same statement for additive character sums. That's 4.3 theorem. Let psi in FQ hat be an additive character, non-trivial. G in FQX of degree n. And without loss of generality, we can assume that G of 0 is 0 because it's an additive character. We can just ignore the constant term. And we need that either the simple root is to say that n and q are coprime, or, so this is needed to make sure that the character psi is non-trivial, or it suffices, you can take a more general, so it's possible to take a more general condition, but then the proof is a little harder, or more generally, z to the q minus z minus g of x, absolutely irreducible. Okay, and then we get again a best possible bound, some psi of g of x, x in fq is bounded in absolute value. And again, this is an honest inequality, no analytic number theory, no implied constant. Well, there is an implied constant, but it's absolutely explicit. It's n minus 1 times square root q, which is even correct for a linear polynomial, in which case it's trivial, and you get by orthogonality of characters 0, but this is consistent. All right. Okay, the proof is essentially the same. So as before, consider all the additive characters. So we consider over a suitable extension field for an arbitrary additive character, the sum over all fq to the nu, psi tilde composed with the norm g of x. And again, we know this is a sum of n minus 1 things, omega j psi tilde to the power nu, for non-trivial psi tilde in fq hat. Okay, and now comes the same trick. We compute in two ways. The quantity R nu, which is the sum or the cardinality of all pairs xz in fq to the nu squared, such that z to the q minus z minus g of x equals 0. And this is something I can detect by the trace. So you remember, so the trace is 0 if and only if, so the trace that from fq to the nu down to fq is 0 if and only if the element is of the form z to the q minus z. That's Hilbert 90 if you want. And if this is the case, then you have q choices by Frobenius. So that's q times the number of x in fq to the nu, such that the trace of nu, the trace nu of g of x equals 0. All right. Okay, and this is again something I can detect by characters. So I take the sum over all additive characters, psi tilde in fq hat, all x in fq to the nu, psi tilde composed with the trace of g of x. Because if the trace of g of x is 0, then I get a contribution of q, and otherwise it vanishes. So I just detect q times those elements where the trace is 0. All right. And so here, of course, we single out the trivial character. The trivial character says 1 all the time. So this gives a contribution q to the nu, plus the sum over the non-trivial characters. S nu of psi tilde. Okay, and this again is a sum j from 1 to n minus 1, omega j to the nu psi tilde. Okay, and again, as long as I don't know anything about these omegas, it's hopeless, but I do know something because we have a corresponding counting lemma for R nu. So we know that was 2.4, that R nu is q to the nu plus O of q to the nu over 2. This depends on q and it depends on g, but it's uniform in nu, and that's the important point. Now we can use our self-improving lemma. The implied constants simply disappear for free. So this improves itself. And we get omega j psi tilde is bounded by q to the 1/2. Okay, and that's it. So a character sum is a sum of n minus 1 things, each of which is of size square root q. Okay, that's how it goes. And you see, I mean, maybe you're now disappointed because you wanted to see mixed character sums. I only treated additive character sums and multiplicative character sums separately. Well, you can guess what would be the input for mixed character sums. For mixed character sums, you would need a counting lemma that can handle not algebraic curves, but algebraic surfaces. Okay, so how would this go? Remark. This can be generalized to mixed sums sum x in fq, chi of f of x, psi of g of x, provided, and in fact we can even allow f and g rational functions. We don't need to have polynomials. This requires a bit of extra work, but it's not so difficult. Provided we have a counting lemma for x, y, z in fq cubed, so or q to the nu cubed, with y to the d minus f of x equals 0, and z to the q minus z minus g of x is 0. So now it's 2 equations in 3 variables. And this requires, I mean, this you can also use auxiliary polynomials, but this is a bit more complicated. Again, I refer to Schmidt's book, where this is all worked out along similar lines, but it's a bit more complicated. Okay, what you get in the end is, so one typically obtains a bound q to the 1/2 times a constant. And now it's, of course, well, what is this constant about? A constant somehow measuring the singularities. Measuring the singularities. Yeah, which is poles and zeros. We will later see this when we look at Klostermann sums. So basically, the numerology for n and m in this. So here, I mean, typically we get n plus m minus 1. This basically counts the poles and zeros of this polynomial. Of course, the degree is like the poles at infinity, something like that. Yeah. Anyway, so something like this, but this is a bit more complicated. In any case, we'll need this in a moment in a special case. So let me just say that, of course, by the same argument as before, this set here equals the sum over all multiplicative, over all additive characters times the sum over all multiplicative characters fq star hat, just by orthogonality of characters, such that chi tilde to the power d is the trivial character, chi tilde nu f of x times psi tilde nu g of x, plus, I forgot the zeros, so plus the terms where f of x equals 0, psi tilde nu g of x. And if both chi and psi are trivial, then I get a contribution q to the nu. And this is the main term, and I'm left with psi tilde, chi tilde, not both the trivial character. And of course, chi tilde to the d equals 1, s nu of chi tilde, psi tilde. Okay, and again, we know that this is a sum of n plus m minus 1 to the power nu things. Okay, this is badly written. All right, so if we have a way, an alternative way to count star, then we get information on the roots, and then we get information on the character sum. And I want to show you this in one particular example, maybe the most interesting example, namely Klostermann sums. Oops. So here is a complete proof for Wales bound for Klostermann sums. All right. So let A, B be two non-zero parameters. Okay, I cheat a little bit. I assume that Q is odd. I don't want to deal with even Q. Although it's not hard, it's just a little more painful. And psi, a non-trivial additive character. Then for the Klostermann sum S, which is sum psi of AX plus B over X, X in FQ without 0. So that's the standard Klostermann sum over a finite field. We have S is bounded by 2 times square root Q. By the way, this is really a finite field, not a finite ring. If you want to bound Klostermann sums modulo q squared or modulo q cubed, then algebraic geometry can do nothing for you. Then you use Taylor expansion and p-adic stationary phase. Yeah? This is a bit technical, but conceptually in some sense easier. It's in somehow just analysis. You compute the derivative and then look at zeros. These are the stationary points. You plug them in and that's it. Okay. Here's the proof. All right, and the trick is we use a little trick. We transform this Klostermann sum a little bit to make it. So the first problem is that this is, I mean, it's only an additive Klostermann sum, but it's only an additive character sum, but it contains a rational function, not a polynomial. I want to convert this into a polynomial. So I take the quadratic character, the unique non-trivial quadratic character of fq star, and here I use that q is odd. The quadratic character of fq star. Then S is the sum over all x in fq. Okay, psi of x, and now I count how often is ax plus b over x a given value. So now I count all the y's in fq star such that ay plus b over y equals x. So I just sort the sum by common values of ax plus b over x, or ay plus b over y. Okay, and this is a quadratic equation, and I just want to know how often does this happen. And I can find this out using the quadratic character and the discriminant of this quadratic equation. So this is the sum over all x in fq. Psi of x times, I take the quadratic character, and the discriminant tells me, so whether it depends on whether the discriminant is a square or not. And the discriminant of this quadratic equation is x squared minus 4ab. And if it's a square, then I get two solutions. The character says 1, so I need to add 1. If it's 0, I get one solution. The character says 0, so again I have to add 1. And if it's a non-square, I get no solution. The character says -1, I add 1, I get 0. So that's what I want. Okay? All right, but the +1, of course, is irrelevant. The +1 can just go away, because if I sum this against psi of x, because psi is non-trivial, the 1 goes away. So this is just fq psi x chi of x squared minus 4ab. Okay, so far so good. Now I'm in the situation of a mixed character sum. So it's a trade-off. I traded the rational function for polynomials, but the price I have to pay is that now it's a mixed character sum. But the nice thing is that the polynomials are very simple. So we have g of x equals x, and f of x equals x squared minus 4ab. In particular, g of x is linear, and solving an equation, a linear equation, is something that we learn in kindergarten. So that's not so terribly difficult. And that's what I use here. So we get a bound. So here we see n is 1, m is 2. So we get a bound n plus m minus 1 is 2 times square root q, provided we have a counting lemma. Provided that we can prove the number of all x, y, z in fq to the new cubed, such that y squared equals f of x, which is x squared minus 4ab, and z to the q minus z minus g, which is just x, equals x. So this should be q to the nu plus O of q to the nu over 2. With some dependence. For instance, this may very well depend on q. All right. But you see, the point is that this is linear in x, so we can simply substitute this into here. And so this just equals the number of all yz in fq to the nu squared, such that y squared equals z to the q minus z squared minus 4ab. Okay, and this is now another polynomial. Let's call it capital F of z. And here we can use our original counting lemma, provided that this polynomial is absolutely irreducible. So we are okay if y squared minus f of z is absolutely irreducible. All right, is this the case? Well, if it was not absolutely irreducible, then, okay, I mean, absolutely irreducible is a property that is only interesting over the algebraic closure. So I can factorize f of z. So if not, then consider y squared minus, so yeah, okay. Well, let's do it differently. So note that f of z factorizes into zq minus z minus square root 4ab times z to the q minus z plus square root 4ab over fq bar z. And these two polynomials, so these two factors, are obviously coprime because they differ only by a constant. So if f of z was a square, then every factor has to be a square by unique factorization. So if y squared minus f is not absolutely irreducible, then each factor must be a square. Then zq minus z minus square root 4ab is a square. Well, but this is not very likely to be true because q is odd, and a square should have even degree. But q is odd. Contradiction. Okay, so that's the proof for closed-Riemann sums. Again, so I mean, this uses a trick. If you had more general theory available, you wouldn't have to use the trick. Here's a superfluous parenthesis. But I showed you how to transform the rational function into a polynomial then for mixed character sums, and because the polynomials are so easy, we can solve the counting problem by hand. Okay, that's basically all the material that I wanted to tell you. And let me just summarize the central ideas. Central ideas and outlook. So first of all, bounding multiplicative or additive character sums is equivalent to counting points on y to the d minus f of x equals 0, respectively, z to the q minus z minus g of x equals 0. Secondly, this point count can be established using auxiliary polynomials, the polynomial method. The cardinality of solutions can be obtained by the polynomial method using auxiliary polynomials of controllable degree, having zeros of high order at all the points of interest. And here we can be sloppy in auxiliary parameters, and bootstrap by passing to extension fields. All right, I was asked why, in one of the earlier talks, why I focus on equations like y to the d minus f of x, simply because this is what you need for character sums. But of course, you can look at arbitrary two-variable polynomials or even multivariable polynomials. So generalization. Count the number of x1 up to xn, so you can look at n variable polynomials in fq to the power n, such that sum f x1 up to xn is 0. This is of interest, for instance, if you have character sums in more than one variable, multidimensional character sums, then of course you need also polynomials in more variables. And this becomes, of course, more complicated. At this point, you can probably not avoid to use at least a little bit of algebraic geometry. And what is proved in Schmidt's book is that this is q to the n minus 1 plus O of q to the n minus 3 over 2. So this is maybe not the best in general, supposing that f is maybe absolutely irreducible. I mean, you need at least some reasonable assumptions. So f is absolutely irreducible. You may be disappointed by the quality of the error term. It saves only a half power of q. Maybe you'd have dreamt that you get something like n over 2 or something like that. This is in general not possible because there can be somehow lower dimensional strata. But okay, that's a general result that's proved in Schmidt's book. Okay, I should also say that I said this earlier. This was historically, this was really motivated by Tuo's results in transcendence theory, and Stepanov used this as somehow as a motivation to apply this for character sums. And the lecture notes that, I don't know if they are already posted or not, but they will be posted at some point. They contain the original source. So I just see there are questions in the chat. Oh, okay. So sorry, I didn't look at them. Okay, I'll read them in a moment. For now, I think it's time to stop. Thank you very much to all of you for coming, for your attention. And yeah, that's the end of this little mini course, and it's the end of the summer school. And maybe it's also, for me as an organizer, it's also a good opportunity to thank all the speakers of this summer school for their contribution.